Hi, I am Tianyu Li. I'm the Data Acquisition Project Leader at Michigan State University for my racing team. In this video, I will show you two most important projects this year on the electronic system. Hi, the first project I have this year is to put analog camera on our race car. Because in previous years, our team is very limited on analog inputs. So I started researching online and find this Texans analog camera. It has 8 analog inputs, 2 digital inputs to 3 CAN IDs at 200 Hz. It is small and lightweight, but it is too expensive because we need at least 26 extra analog inputs on our car. So having 4 of this is too expensive for us, and I started to design my own analog CAN converter. So this is an analog CAN converter that I designed for our race car. You can see it is larger and about twice heavier than the Texans analog CAN converter. It has 20 analog inputs, and the microcontroller is fast enough to fill the baud rate of the CAN bus. So having 2 of this on the car is a lot less cost, and the total weight is about the same as 4 Texans analog CAN converters, and we have a lot more flexibilities because it is fully programmed in C, and I can choose any sending rate of the CAN messages up to 2700 Hz. Here is the flow chart for the main circuit on the analog CAN converter. The microcontroller I choose is TNZ 3.1. It has 20 analog inputs at 10 bits from 0 to 3.3 volt scale. The voltage range of the sensor on the race car is 0 to 5. So I have this op amp circuit to convert 0 to 5 voltage ratio or voltage scale to 0 to 3.3 voltage scale. Then for the microcontroller to read. And MCP 2551 is used to convert everything into CAN messages. The whole analog CAN converter gets 12 volt directly from battery. The power consumption is very low. Average only draw 95 milliamp of current. And there's 2 voltage regulators on board, providing 5 and 8 volt sensor power supply, also sensor ground. It's oscillation prevented, and max current draw for each circuit is about 1 amp. It features a lightweight 3D printed housing. So with this analog CAN converter, we have a lot more flexibility at a very low cost. Because this is the first year, I put a fully customized CAN bus on a race car. So I try not to put any engine control related over the CAN bus, so that, for example, when anything on the CAN bus failed, our car is still able to drive, and the driver can drive the car and finish the endurance. The worst case is just not logging any data. So here, I'll put the brake light, for example. It's pretty easy. Same microcontroller and MCP 2551, read and decode over the CAN bus, send a signal to the low side driver, which is basically N-channel MOSFET, and the driver drives the LEDs to light up. Here is another important project I had this year. This is a power distribution module we have on the car for all electronic devices. We don't buy one from Lotec because designing our own one gives us more flexibility, and I can put ignition modules here, so we don't have to buy another ignition module, which saves a lot of budget for the team. These are solenoid drivers for shifting circuit, clutch, downshift, upshift. Each solenoid has one. Here are protection signals and flipping gates for flipping logic. Major circuit goes here. Battery positive goes here. This is starter outputs, and this is the ground side of the battery. Here is a here is a diagram for the main circuit of the PDM. Everything gets power from the main switch, which is required by rule, to the battery positive, and everything gets signal from where needed. Protection for open wire, which is pull up or pull down resistors. Logic gates for flipping the signal if needed. Goes to a high side driver, which is basically MOSFET. And each circuit is isolated and separate by itself. And all the reset fuse is used for each circuit. Fuse size I selected by testing after the whole system is made, and I go back and validate the design and choose the specific size of fuse. Load devices have a diode for inductive loads, for example for pump fans. Here is a diagram for all the circuit on the power distribution module. The starter circuit and the main circuit gets its signal from ECU ground, so when ECU is disconnected, it won't trigger. Here is the main switch on the side of cockpit, which is a panic button. So when it's killed, the main circuit won't get signal and ECU won't start. It will kill the engine. And the data circuit is short to that, so as I mentioned before, when something wrong with the data circuit, I want the ECU maintain functioning so we can still finish the race. The next circuit is the fuel circuit, which has all of our fuel injectors, shifting solenoids, ignitions, everything on it. It also goes through the panic button, which is a double pro single throw switch, goes through a fuel switch and a breakover channel switch. So when one of these switches is flipped, it will kill the engine too. The first circuit is the general diagram for all PWM circuit. It gets signal directly from AUX output of the ECU, which is a PWM signal, and drivers directly drive the pump and fans. Here's a diagram of ignition circuit. Everything gets power from fuel circuit. The ignition coils are driven by IGBTs, and it gets signal from ECU and open wire protection, pull down resistor here. The shifting circuit is the same idea. Solenoids get power from fuel circuit, low side driver used to drive it, protection for open wire, and gets signal from ECU. So this is about it. Two most important projects I have this year. I also have a lot more little side projects I've done. It's on my resume. I'm always happy to answer any question about them. But there's one more little project I want to mention here because it directly validates my design for the power distribution module. It's basically a simple current sensor board having 4 Hall effect sensors, analog voltage from 0 to 5 scale, directly send it to the analog CAN converter so I can log it real time with the car is running. This directly is the data, directly validate my trace width selection and fuse selection, also the wire selection, wire size selection I have on the car, and I'm able to get a full curve of the our pumps and fans on the car at different duty cycle of PWMing, and it also helped me on a rectifier selection, and I find out actually the aftermarket rectifier we found online is worse than the OEM one, so it is pretty helpful and means a lot to the PDM. So thank you for watching the video. I'm always happy to discuss any design. Also, I'm looking forward to improve all my design next year. For example, I want to make my own electronic fuses on board on the power distribution module to shrink down the weight and size. Also, I want to put little soldering pads for the analog CAN converter for the temperature sensors, so I don't have to solder pull up resistor in wires like I have this year. Also, I'm looking into filtering and making my own specific microcontroller on board to even shrink down the size of it and packaging. I'm always happy to answer any question about my design And also, if you can help me on future design or discuss about it, I'm always happy to do that too. So thank you very much for watching the video.